All right. Hello, everyone. In this presentation, I'm going to be discussing changes we made in Ruby 3.3 and 3.4 to reduce implicit allocations during method calling. So my name is Jeremy Evans. I'm a Ruby committer who focuses on fixing bugs in Ruby. I'm also the author of Polished Ruby Programming, which was published in English a few years ago and was published in Japanese last year. And this book is aimed at intermediate Ruby programmers and focuses on teaching principles of Ruby programming, as well as trade-offs to consider when making implementation decisions. Now, if we want to reduce implicit allocations, the first step is to measure the implicit allocations. If you do not know how many objects a method call implicitly allocates, you cannot determine whether it is possible to reduce the number of allocations. So here is a method that displays how many arrays and hashes are allocated inside a block. Now, unfortunately, I don't have enough time to fully explain how this works, but the important part is you can call the object's allocated method with a block, and it will print the number of arrays and hashes allocated by the block. And using this object's allocated method, we can examine how many objects are allocated for certain types of method calls. So the first allocation reduction optimization that we're going to examine, I'm calling keyword splat separation. And this technique was implemented by Sasada-san early in the Ruby 3.3 development cycle. So we're going to consider this code example. We're going to call an empty method that takes no arguments. We're going to create an empty array in a hash, and we're going to splat the array and keyword splat the hash when calling the method. Now, any guesses as to how many objects are allocated by this method call in Ruby 3.2? No guesses. Turns out Ruby 3.2 allocates 4 arrays and 1 hashes for this method call. And considering that delegating arguments to other methods is commonly done via splats and keyword splats, this unnecessary object allocation can result in significant slowdowns. Now, Ruby 3.3 fixes this, avoiding any allocation for this type of call. We can examine why this type of call allocates so many objects in Ruby 3.2. We can run Ruby with the dump instructions option, which will dump the virtual machine instructions used. And we'll pass the code to evaluate with the E option. So these are the simplified dump instructions. The method call starts with put self and ends with the second op send without block instruction. So let's go through these instructions and see where the allocations are. So the first array allocation during the method call is for splat array true, which will duplicate the array local variable. This new hash instruction allocates a new hash, and this instruction copies the contents of the keyword hash into that newly allocated hash. This new array instruction wraps that newly allocated hash in a newly allocated array, and this concat array instruction allocates new array when concatenating the array containing the new hash to the array produced by splat array true, even though splat array true has already allocated a new array for this purpose. However, something does not add up here. So these instructions should only result in 3 array allocations and 1 hash allocation. So where does the final array allocation take place? And the final array allocation is on the callee side of the method, which duplicates the array of arguments because it is going to remove the empty keyword splat from the array. Ruby 3.2 basically treats code like this, with a positional splat and a keyword splat, as a splat of a single array containing both the keyword splat and the positional splat. And it wasn't really efficient about allocations when it was doing this. As I mentioned, Sasada-san fixed this in Ruby 3.3. So if you generate the instructions in Ruby 3.3, you get much simpler instructions because the positional splat and the keyword splat are separated. Because the keyword splat's not combined into the positional splat array, the callee side doesn't need to remove the keyword splat from the array, so it avoids the callee side array allocation. Now, my first change to reduce implicit allocations was making this particular change. So after Sasada-san's changes, this instruction still used splat array true, which will allocate a new array. And I determined it was unnecessary to allocate a new array in this case, because Ruby is no longer appending the keyword splat to the array. So I changed it to use splat array false, and that made the call allocationless. And as I was working on this fix, I saw that it affected other cases, and I decided I wanted to do something about this issue. First, I decided on a goal that I think Ruby should have regarding implicit object allocations. That goal is to have no unnecessary allocations. I think Ruby should only allocate an object if it is necessary to do so. And this goal has two corollaries. The first corollary is that Ruby should allocate at most one array implicitly during method calling. There are cases when Ruby needs to allocate an array, such as for a positional splat parameter, but there should be no reason to allocate multiple arrays implicitly. Similarly, the second corollary is that Ruby should allocate at most one hash implicitly during method calling. A keyword splat parameter may require a hash allocation, but there should be no reason to allocate multiple hashes implicitly. My first steps towards reducing allocations were to fix additional cases where Ruby was using splat array true, which allocates, when splat array false would work, since an array allocation was not necessary. So here is an example where Ruby 3.2 did not need to allocate any objects during a method call. We have a method that accepts an optional positional argument. We call that method with a positional splat. Even in Ruby 3.2, this does not allocate any objects. Now, if you change the call to pass both a positional argument and a positional splat argument, then Ruby 3.2 will allocate an array. And the cause is the same as the previous example, where Ruby 3.2 will use splat array true instead of splat array false. So I assume the fix would be similar. When I first started working on these changes to optimize splat array, I tried to make the changes directly in the compiler. And I found that ended up being challenging. The compiler is the third step in converting your Ruby source code into virtual machine instructions. So the first step is the lexer, which takes your source code and separates it into a stream of tokens. The second step is the parser, which takes your token stream and builds an abstract syntax tree. Compiler takes your abstract syntax tree, builds a list of virtual machine instructions. And there's a fourth step, the optimizer, which takes the list of virtual machine instructions generated by the compiler and potentially modifies the instructions to use more efficient instructions that have the same effect. Now, if you want to optimize code, depending on the abstract syntax tree, those changes are best made in the compiler. But if you want to optimize code for all cases where specific combinations of instructions are used, regardless of the abstract syntax tree that generated the instructions, those changes are best made in the optimizer. So for this method call, these are the virtual machine instructions. And to remove the unnecessary array allocation, we need to change splat array true to splat array false. However, you can't just change splat array true to splat array false in all cases. There are cases where splat array true is necessary for correct behavior. So for the optimization to work correctly, you need to look at what instructions follow the splat array instruction. So if the splat array instruction is followed directly by a send instruction, and that send instruction supports an argument splat, but does not use keywords or a block, then it's safe to change splat array true to splat array false. So to implement the change of splat array true to splat array false, I added the following code to the optimizer. So I'm going to walk through each part of this code. The way the optimizer works is it goes through every generated instruction. Now, the optimization we added does not need to consider these instructions. So during the optimization pass, these would be ignored by the new optimization. This is the instruction we want to change, splat array with an argument of true. So in the optimizer, we check, is the current instruction a splat array instruction? And if so, does it have an argument of true? And these are potential candidates for switching the argument to false, assuming that doing so is safe. Now in this optimization, we only want to change the splat array instruction argument if it's followed directly by a send instruction. So the optimizer checks if the next instruction is a send instruction. Now there's a disconnect here, because the instruction shown in the output is opt send without block, and the instruction that the optimizer code is checking for is send. And the reason for this disconnect is the instructions I'm showing you are the instructions after optimization, not the instructions before optimization. So when working in the optimizer, it's often useful to get Ruby to output the instructions before optimization, which you can access via the instructions without opt argument for the dump option. Note that this dump option value is changing in Ruby 3.4, so in Ruby 3.4 you'll need to use this value for the dump option. So here are the instructions for the method call before optimization. The change from send to opt send without block happens in a later optimization pass. So at the point that this optimization is running, the instruction is still send, so it will match. Now this code extracts the call info flags from the method call. And these are the call info flags, which contain information about the method call. Arg splat means the method call uses a positional argument splat. Fcall means the method call does not have an explicit receiver or the explicit receiver itself. Send instructions with the fcall flag are allowed to call private methods. We're looking for instructions that have the args splat call info flag, so the optimizer code checks for that flag. And additionally, this optimization is only safe if the method call does not pass keywords or a block. So we need to check that those call info flags are not present. And finally, to eliminate the array allocation, we update the splat array instruction argument to false. And that makes this call allocationless. So all of that code was added to avoid the unnecessary array allocation in this case, where you had one or more positional arguments followed by a positional splat with no keywords and no block. If a block is passed, that case needs to be optimized separately. So the instructions generated in that case look like this. Between the splat array and the send instructions, there's an instruction to get the local variable for the block. And when checking the send instruction call info flags, you need to check for the presence of args block arg instead of the absence of the flag. Note that this optimization is only used if block is a local variable or an instance variable. It's not used if block is a method call. And the reason for that is if block is a method call, calling the method could result in a modification of the splatted array. And modifications to the object after it has been splatted should not have an effect on the splat. In addition to these two cases, there were some other cases optimized. For lack of time, I'm just going to go over these cases without discussing the instruction changes for each. So the next case is when a positional splat is followed by a keyword splat. So I mentioned this case earlier when discussing keyword splat separation. I originally developed the optimization for this case as a compiler change, but I switched it to an optimizer change after working on the optimizer changes for these other cases. The next case is when a positional splat, keyword splat, and a block are all used. And the next case is when a positional splat is followed by literal keywords. Now this is actually similar to the keyword splat case, because in Ruby, if you have a positional splat and literal keywords, the literal keywords are treated as a keyword splat. The only difference is that Ruby uses a different instruction to generate the keyword splat. So the final splat array optimization was when a positional splat, literal keywords, and a block are all used. Now unfortunately, it turns out that optimizing these cases of a literal keywords after a positional splat caused a bug. If a method call accepts a positional splat parameter but does not accept keywords, then the hash for the keyword splat would be appended to the argument being splatted instead of a copy of the argument. Now this issue was hidden before because Ruby would duplicate the positional argument splat on the caller side. I fixed this case by duplicating the positional argument splat on the callee side. I mentioned earlier that optimizing this case of a positional splat followed by a block could result in issues if block is a method call, because calling block may modify the positional splat argument. This type of issue is called an evaluation order issue. So during this optimization work, I found that this type of call with a keyword splat in a block also had an evaluation order issue. Because if the keyword splat argument was not a hash and the block was not a proc, block.toProc would be called before keyword.toHash. Ruby 3.2 would generate the following instructions for this method call. Both block.toProc and keyword.toHash would be called inside the send instruction, but block.toProc would be called first. So I fixed this case by adding a new instruction named splat keyword, which is issued directly before send instructions that have both keyword splats and block arguments. And if the keyword splat object is not a hash, it will call toHash on it, ensuring that keyword splat.toHash is called before block.toProc. Unfortunately, fixing this bug broke some of the optimizations I worked on previously. I didn't actually fix those cases until after the release of Ruby 3.3. While analyzing additional cases to fix, I found that supercalls with explicit arguments also had this evaluation order issue, so I fixed those as well. And I also found that you could pass both a keyword splat and a block using operator assignment syntax. However, this would result in a type error exception being raised, which is kind of weird, and that was even true of not passing a block. And if you passed literal keywords when using operator assignment syntax, it would segfault the compiler. I fixed all of these cases, so all of these work great in Ruby 3.3. Now, support for both blocks and keywords has been removed from the operator assignment syntax, so these will all result in a syntax error in Ruby 3.4. Another bug I found when I first started working on the splat array optimizations was introduced by keyword splat separation, and it affected this code. Here we have a plain object. We define a toHash method on the object that returns a hash. And you call the method with a positional splat and a keyword splat of the object containing toHash, and the method accepts both a positional splat parameter and a keyword splat parameter. Ruby would call the toHash method on the keyword splat argument to check that, yeah, it returns a hash, but it would use as the value of the keyword splat parameter, it would use the keyword splat argument, not the hash generated by toHash. Now, once I found this, it was easy to fix by using the result of toHash as the keyword splat parameter instead of ignoring the result of the toHash method. And the final bug I discovered during this optimization work was actually introduced by my keyword argument separation changes in Ruby 3.0. We have a method that accepts the object that has been passed. We call the method with an empty positional splat and a keyword splat. The return value of the method is a copy of the keyword splat, which is what you would expect. But if you called the method with a keyword splat and no positional splat, it would pass the keyword splat argument directly instead of making a copy of it, as if you would pass the keyword splat argument as a normal positional argument. Now, this behavior makes no sense and goes completely against keyword argument separation. But it turns out there were actually specs added for this, making people who reviewed the specs think that this was the desired behavior. Now, thankfully, fixing this was approved, and it was easily done by copying the keyword splat hash on the callee side of the method. So up to now, all the optimizations that I've been discussing are available in Ruby 3.3. The rest of the presentation is going to discuss some of the implicit allocation reduction optimizations I worked on that will be in Ruby 3.4. So I'm going to start with this example. This passes multiple positional splats when calling a method. And the method itself has a positional splat parameter. In Ruby 3.3, this allocates 3 arrays. So here are the instructions generated for the method call. The first thing to be aware of is that Ruby's internal method calling API does not support multiple splats. It only supports a single splat. So Ruby implicitly combines your multiple positional splats into a single array and then calls the method with a splatted version of the generated array. So the first array allocation during this method call is for splat array true, which will duplicate the array local variable for the first positional splat. And you cannot eliminate this allocation because Ruby does need to provide a single array to splat, and it can't modify either of the splatted arrays. The second positional splat uses the splat array false instruction, which does not allocate an array. Ruby combines the two positional splats into a single array. And the instruction it uses for this is concat array. If the first positional splat is already an array, concat array will make a copy of that array before concatenation. And this is the second array allocation. Now, this allocation is unnecessary because Ruby already allocated a new array in the splat array true instruction. And the final array allocation is on the callee side of the method, and that's because the method accepts a positional splat parameter. And positional splat parameter values should never be the same object as the positional splat argument. So Ruby duplicates the positional splat argument when setting the positional splat parameter value. Ruby's method call interface did not support the ability for the caller to tell the callee that I've already generated or allocated a new array for this. So I first worked on removing this unnecessary allocation. To eliminate this allocation, I added an argsplat mute call info flag. And this call info flag is what allows the caller to tell the callee that, hey, I've already allocated a new array for the positional argument splat, you can use it directly. So with the argsplat mute optimization, this makes the call only allocate 2 arrays. But that's still more than the goal of at most 1 array allocation. I mentioned that you cannot eliminate the array allocation for splat array true, because Ruby does need to allocate an array on the caller side. So to achieve our goal, we need to eliminate the array allocation for concat array. Now, unfortunately, Ruby did not have a virtual machine instruction other than concat array for combining arrays. Now, there were 2 possible ways to fix this. One way is to have the concat array instruction require an argument, which it could use to determine, do I need to duplicate the array being concatenated to? And the main issue with this approach is it's invasive, because all of the calling code needs to be adjusted. And when all of the calling code was only in the virtual machine, this wasn't as much of a problem, but now that Wigit does a great job at optimizing all of our virtual machine instructions, you would need to make changes both in Wigit and in the virtual machine. Additionally, this approach is also slower because it requires checking the instruction argument value. So I did not use this approach. Instead, I chose to add a new instruction named concat2array. And this instruction would be used when you are directly mutating an existing array when concatenating, and it could assume that the array being concatenated to is already an array, which saves an additional type check. So with those changes, the method call that used to allocate 3 arrays in Ruby 3.3 now only allocates a single array, which achieves our goal. So now that the multiple splat case was optimized, I moved on to the next case, which is where a positional argument follows a positional splat. Surprisingly, this allocates more arrays than the multiple splat case in Ruby 3.3 with 4 array allocations. And here are the instructions generated for this method call. If you notice, these are exactly the same instructions that are used in the multiple splat case, except for this new array instruction. So the reason for this instruction is that Ruby did not have a virtual machine for pushing an object onto an array. So any cases where Ruby needed to push an object onto an array, it would wrap the object in a new array and then use concat array to concatenate the arrays together. Ruby basically treats the method call like this, wrapping the argument after the splat in a separate array before combining it. So the previous optimization for mutable positional splats already removed the callee side array allocation, bringing this down to 3 total array allocations. I could have switched the concat array instruction to concat2array and bring it down to 2 instructions, but then I would not have been able to eliminate this new array instruction allocation. And that means we could not achieve our goal of at most 1 array allocation. So to achieve our goal, we need to eliminate the allocation for both of these instructions. And I achieve that goal by adding a push2array instruction. And this instruction is similar to the new array instruction in that it pops the given number of objects off the VM stack. But instead of creating a new array with the instructions, it pushes each of the objects from the array that you popped off the stack to the array that's then currently at the top of the stack. In that case, this is the array created by splat array true. So with the combination of argsplat mute and push2array, Ruby 3.4 will only allocate a single array for this call, which achieves our goal. In this example, we have a method that accepts a positional splat parameter. And it's not possible to avoid allocating an array for this parameter. It's because any code inside the method could, theoretically, access this C variable. And while working on these optimizations, I realized you could remove the ability to access the variable, then Ruby would be possible to avoid the allocation. Turns out that Ruby already supports that, using the anonymous splat parameter syntax that was introduced in Ruby 3.2. Now, technically, using anonymous splat parameters was supported in earlier versions of Ruby. What Ruby 3.2 added was the ability to use the anonymous splat parameter as a splat argument when calling other methods. And this was supported both for keyword splats in addition to positional splats. So here's an example with anonymous splat parameters. We have a method that accepts a positional argument and a keyword argument. We have a method that delegates all positional arguments and keyword arguments to that method using anonymous splats. When we call the method with a positional splat and a keyword splat, we see that Ruby 3.3 allocates both an array and a hash. And the array is allocated for the anonymous splat parameter, and the hash is allocated for the anonymous keyword splat parameter. Both of these allocations are unnecessary, because we can be sure that the method is not able to access the objects directly. It can only pass them as splats when calling other methods. So my next task was to eliminate these allocations. To do so, I first needed to track whether the method uses anonymous splats or not. And the easiest way to track that is to use ISEC parameter flags. So for every method that you write in Ruby, there's an instruction sequence, or ISEC. And each of those ISEC methods has a set of parameter flags. So the G method in this example has 2 parameter flags set. The hasLead flag is set because the method has a mandatory positional argument, and the hasKeyword flag is set because the method accepts a keyword argument. For the F method, the hasRest flag is set because the method accepts a positional splat, and the hasKeywordRest flag is set because the method accepts a keyword splat. So to start the optimization process, I added in a non-rest flag, since the positional splat is anonymous, and I added in a non-keyword rest flag, since the keyword splat is anonymous. And then I implemented the anonymous positional splat optimization. So when calling a method with a positional splat, if that method has the non-rest parameter flag set, and it's possible to use the positional splat argument directly as the positional splat parameter, the duplication of the positional splat argument is eliminated. Note that it's not always possible to use the positional splat argument directly. If the method you're calling accepts a mandatory positional argument, but you didn't provide it separately when calling the method, you cannot eliminate the allocation because you need to remove the first element of the splatted array because that element becomes the positional argument parameter. And next I implemented the anonymous keyword splat optimization. So if you're calling a method with a keyword splat, when the non-keyword rest flag is set and the method does not have named keyword parameters, this avoids the duplication of the keyword splat hash. So with those changes, Ruby 3.4 will not allocate any methods for this type of call. One of the nice things about this optimization is it works even with multiple levels of indirection as long as each level uses anonymous splats. So if you add a level of indirection via an H method, which uses anonymous positional and keyword splats and delegates to G, and you change F to call H instead of G, Ruby 3.3 would allocate 2 arrays and 2 hashes, 1 for each of the indirection levels. But Ruby 3.4 would still not allocate any objects for this method call. In Ruby 3.2 and 3.3, using anonymous parameters was purely for nicer syntax. But starting in 3.4, it offers better performance in some cases, which grants Ruby users an additional way to optimize their code. I really like this optimization. I've given it a name, Allocationless Anonymous Splat Forwarding. The final optimization I will discuss is related to generic argument forwarding. So if you switch these anonymous splats to use generic argument forwarding, Ruby 3.3 would allocate 3 arrays and 3 hashes. And the reason this uses more arrays and hashes in Ruby 3.3 is that generic argument forwarding is implemented via Ruby 2 keywords, which is not as well optimized as separate positional and keyword splats after keyword splat separation. So I switched generic argument forwarding to use an anonymous keyword splat internally, and Ruby 3.4, these calls are also allocationless. So here are a couple of closing thoughts related to my experience working on these optimizations and fixing the bugs I discovered during this process. First, working on optimizations is a great way to find new bugs. To optimize code, you really need to understand how the code works, and once you understand how the code works, the cases that could be problematic often become more obvious. Second, once a bug is found, fixing that bug takes priority over the optimization work. I discussed in this presentation the Ruby 3.3 optimizations before the bug fixes, but the bug fixes were committed either before or at the same time as the optimizations. We must always remember that performance comes after correctness and not before. I hope you had fun learning about the implicit allocation reductions in Ruby 3.3 and 3.4. There are a bunch of additional allocation reduction optimizations I worked on that will be in Ruby 3.4. So possibly there'll be a part 2 of this presentation in the next RubyKaigi. If you enjoyed this presentation and want to read more of my thoughts on Ruby programming, please consider picking up a copy of Polished Ruby Programming. And that concludes my presentation. I'd like to thank all of you for listening to me. Special thank you for Shopify for sponsoring my travel to RubyKaigi.